AB Calculus, Section 4.1, Maxima and Minima. The definition of absolute maximum and minimum values. Let F be defined on a set D, this is kind of like the domain of the set, containing x equals c. If f of c is greater than or equal to f of x for every x in this domain, then f has an absolute maximum value of f of c on that domain at x equals c. Let's make a sketch here real quick. All right, let's say that the domain is from -2 to 3. And let's say here's f of -2. And there's f of 3. Okay, let's continue reading. If f of c is less than or equal to f of x for every x in that domain, then f has an absolute minimum value. Okay, so as I look at this function, actually I'm going to undo the graph for a moment, and I'm going to make it slightly different. Okay, that's better. I like that. I got a few more things I can talk about now. Okay, let's talk about an absolute max. Right, we would have an absolute max at this value on that interval, right? Let's call that C1. Okay, this would be f of C1. That would be an absolute max because it's the largest output for the function on the interval. I would have an absolute minimum value here at C2. This would be f of C2 because that's the smallest output or the lowest output on that interval. Okay, now absolute extreme values refer to either absolute maximums or absolute minimums. Now a local maximum or minimum is just in a general area what the largest possible value would be. So let's read the definition. Suppose C is an interior point of an interval. Okay, interior point, non-endpoint. That means you can't have local max or mins on an endpoint of an interval on which f is defined. If f of c is greater than or equal to f of x for all x in that small interval, then f of c is a local maximum. If f of c is less than or equal to f of x for all x in that little interval, then f of c is a local minimum. So this would technically be a absolute maximum as well as a local maximum, right? In this little interval around C1, that would be the max value, as well as this would be a local minimum and an absolute minimum. We just refer to them as absolute. Okay, we would also have a local maximum here. We could call that C3, and we would have a local minimum here at what we could call C4. Okay, so those are true local max, local min, because they are not absolutes. All right, so this would be a local extrema, local extrema. All right, the two conditions for absolute max and min to exist is that you have to have a continuous function f of x and it's got to be on a closed interval. Closed interval. So that brings us to the theorem called the extreme value theorem. Oh, that function is just going to carry right along with me, isn't it? Okay, let's try this again. Zoom out. Yeah, there we go. Okay, so the extreme value theorem, what does it say? Let me get that parallel. There we go. This is required knowledge, first of all. It's also called the max-min or min-max existence theorem. A function that is continuous at a closed interval has an absolute max and an absolute min value on that interval. Guaranteed, right? Guaranteed. So let me look at, let me see if I've got more down here. Got it. Okay. So on any closed interval, the function has to take on a max value and a min value. So here's my absolute min on this closed interval from A to B. Right, there we go. That's my absolute min. Here's my absolute max. And then I've got local min, or local max, local min, and then here's just an endpoint that's somewhere in between. So the local extreme point theorem is if f has a local max or min at x equals c, then f prime of c exists, and f prime of c exists, then the derivative f prime at c must be 0. Now you'll see here, local max, local min. If the derivative exists, then it's got to equal 0. Well, what if it doesn't exist? Could there be a local max? Yes. So that means when we check for local or global extrema, specifically when we're talking local, we want to check to see where f prime either equals 0 or f prime doesn't exist when we're seeking an absolute min or absolute max, as well as for local min, local max. All right, let's try a few examples. Okay, so let's use a few steps in order to locate the absolute extreme values on a closed interval. The first thing we need to do is define what's called a critical point. A critical point is an interior point of this closed interval at which either f prime at this value, right, so the critical value would be x equals c, if f prime at that value equals 0 or the derivative fails to exist. This is called the critical points of f. So our steps for locating the extreme values on this closed interval, assuming f is continuous on a closed interval, those two criteria we talked about earlier, locate the critical points. These points are candidates for the absolute max, absolute min. Evaluate f at those critical points and at the endpoints. Choose the largest and smallest values from step 2, and these values are your absolute values. So with step number 1, what that's implying is that we first find the derivative. So in example number 1, it says find the absolute min and max values for the function on that closed interval. So I'm going to first find f prime. I'm going to use my power rule, 4x cubed minus 6x squared. So there's f prime. Now I'm going to put a list of candidates for my extreme values with respect to just x. Okay, my candidates. Well, I know my candidates are my ends. So that would be x equals -2 and 2. So possibly I could get an extreme value or an absolute value of max or min at one of the ends, or at my critical points. My critical points are going to come directly from the derivative. So I'm going to find where f prime is equal to 0. So I set this equal to 0. I'm going to factor out an x squared. That leaves me with 4x minus 6. Okay, now I'm going to solve for where this would equal 0. Well, it would equal 0 where x squared equals 0, which is where x equals 0, or where 4x minus 6 equals 0, which would be x equals 3/2. So my critical points are at x equals 0 and x equals 3/2. Now in this case, the derivative never fails to not exist. That sounds counterintuitive, but the derivative f of f prime of x always exists. Always exists. Why? Because it's a polynomial. Therefore, we don't have to worry about finding the critical values where f prime does not exist. All right, now we've got all the candidates. We've got the endpoints, we've got the critical values or critical points. So now what we're going to do is we're going to find outputs for each of those critical points or candidates, and endpoints. So I'm going to switch back here. I'm going to take my x values of -2, 0, 3/2, and 2, and I'm going to find outputs for each of those. So I'm going to find f of x for each of those values. F of -2 is 32, f of 0 is 0, f of 1.5, I can't fit it in here, but it's negative 1.6875, and f of 2 ends up being 0 as well. So now I have an absolute maximum value. At the point negative 232, and I've got myself an absolute minimum value at the point 1.5 and negative 1.6875. There you have it. That's your first example on how to find absolute minimum and maximum values on a closed interval. Let's do another. Okay, let's try a second example. Non-calculator example. The function f is defined by natural log of x over x for all x greater than 0. Find the max value of f on the interval from 1 over e to e. So as I talk candidates, okay, I've got two of my candidates available to me immediately. They are the endpoints, which are x equals 1 over e and x equals e. So let's find the critical values. So in order to do that, we first find the derivative, which will require for us to use the quotient rule. So I'm going to take the lower function, x, times the derivative of the upper function, ln of x. The derivative of x with the derivative of ln of x, with respect to x is 1 over x. That's not one that we have yet in our pocket. We saw it briefly in previous notes, but it's not one that we have covered formally yet. So just be aware. So the derivative of natural log of x is 1 over x minus the upper function ln of x times the derivative of the lower function, which ends up being 1 all over x squared. Okay, so let's talk about this. Let's simplify a little bit. That'll be 1 minus natural log of x over x squared. So for these critical values, we want our critical points. Let's go there. Yep, critical points. What I want to do is I want to find out, does the derivative, or the first derivative in this case, ever equal 0? And is there a value such that the derivative does not exist? Okay, are there values that satisfy either of those two? Well, in this case, we can see that the derivative does not exist at x equals 0. So we could claim that x equals 0 is a critical point. However, we've worked around that, seeing that x is greater than 0. So now what I want to do is I want to set the first derivative equal to 0. Okay, and the only way that this would equal 0 is if the numerator equals 0. The only way that's true is that if natural log of x equals 1, which means that x would equal e. So we've got one critical value, and that critical value or critical point is actually also an endpoint. Therefore, as I check for my maximum value on the interval 1 over e to e, I just have to check two values. X equals 1 over e and x equals e. Now, I don't have my calculator available to me, so I'm going to evaluate these. F of 1 over e would be the natural log of 1 over e over 1 over e. We'll simplify that in a moment. And f of e would equal natural log of e over e. Okay, so let's do f of e first here, evaluating this. That'd be 1 over e. So the output here is 1 over e. And the natural log of 1 over e, let's simplify this quick, is equivalent to the natural log of e to the negative 1, which is equivalent to negative 1 times the natural log of e, which is negative 1. Therefore, this would be equal to negative 1 over 1 over e, which is equivalent to negative e. So which of those two is a larger output? Clearly f of e would be the larger of the two. And thus that would be our max value. Our max value is not e. Our max value is the output. Okay? Therefore, looks like our answer here would be C. Let's look at another example. All right, let's try another example here from an FRQ back from 2007. Non-calculator example yet again. Okay, we're going to find our candidates, which of course will include our endpoints, which in this case are t equals 0 and t equals 2 pi. Okay, we got to find our critical points. Let's use the derivative in order to determine these critical points. So a particle moves along the x-axis with position at time t given by the following. So x of t gives us the position of the particle along the x-axis at time t. So if I were to draw you a graphic, right, x of 0, right, if we plug in a 0, we get e to the 0 times the sine of 0. So at time t equals 0, the x position of the particle is at the origin. Okay, at time t equals 2 pi, okay, we're going to do the same thing. So e to the 2 pi, negative 2 pi, sine of 2 pi. Now, it's kind of a weird situation. However, it's made very simple. Right? E to the negative 2 pi, what is that? Well, it doesn't matter because sine of 2 pi is also 0. So the position of the particle at time 2 pi is also at the origin, right? At the x value, x equals 0. We'll look at the other two here in a moment once we find these critical values. So let's find x prime of t. So this will be the change in the position of the particle in the horizontal direction. So when x prime of t equals 0, that means that the particle has come to rest, right, horizontally. So it might be moving to the right and then pause and then move to the left. When it pauses, that would be when x prime of t would equal 0. Now in this case, okay, let's go ahead and find the derivative here. We're going to use the product rule. So the derivative of the first will be negative e to the negative t times the second left alone plus the first left alone times the derivative of the second, which is cosine of t. All right, so I want to know where that's equal to 0, and I want to know if that ever is non-existent. Now, since both e to the negative t, sine of t, and cosine of t are continuous for all values of t, then we know that x prime of t always exists. So this is kind of like the previous example. F prime of t, x prime of t always exists. So I'm not worried about this ever happening. I'm never worried about that in this case. Therefore, I can be confident that my critical values or critical points will come from finding where x prime of t equals 0. So before I rewrite that whole expression, I'm going to factor out an e to the negative t. And then I'm going to rewrite the inside as cosine of t minus sine of t. Okay, so I rewrote that. Now, I want to know then where either this equals 0 or where this expression equals 0. Now, where cosine of t minus sine of t equals 0 is where cosine of t is equal to the sine of t. Right here. Good. There we go. Now, if you looked at a graph of e to the negative t, it would look kind of like this. And students ask all the time, do I need to know what that looks like? Yeah, you do. Okay, so let's call this y equals e to the negative t. That'll never equal 0, right? Because there's a horizontal asymptote there and it never crosses it. So e to the negative t does not equal 0 for all t in the real numbers. So I'm not going to yield a critical point from that portion of the expression. However, over here, I know that the cosine and the sine are the same, at least between 0 and 2 pi. Right here, let's look at it. So I think pi over 4 is when I see cosine and sine the same, right? However, I get a positive here, so that value will work, pi over 4. Here I get a positive, negative positive, so those aren't. I get a negative, those will be. That's 5 pi over 4. Right, we're not going to use this point. This would be 3 pi over 4 because they have opposite signs. And we're not going to use this point down here, which would be positive negative, which would be 7 pi over 4. Okay, so now we have our critical points, which would be t equals pi over 4, 5 pi over 4. Pi over 4, 5 pi over 4. All right, so we're going to check each of these endpoints. I'm going to put my table vertically. So t and x of t. So we can find, it looks like, question asks, find the time t at which the particle is farthest to the left, which means if I'm looking for farthest to the left, that's an absolute minimum. Absolute minimum. So let's plug some values in. We're going to plug in 0, pi over 4, 5 pi over 4, and 2 pi. Now, we conveniently already found x of 0. That was 0. And x of 2 pi, that was also 0. So we got our endpoints kind of checked off. Let's plug in a pi over 4. All right, so we would take e to the negative pi over 4 times the sine of pi over 4 and e to the negative 5 pi over 4 times the sine of 5 pi over 4. Okay, so really all I'm interested in here is I just want to know what time it happens. I don't care what the actual position is. I want to know what time. Okay, so I'm either going to be, it looks like, well, I guess I don't know yet. I got to find out if my values here are greater than or less than 0. So e to the negative pi over 4 is the same as 1 over e to the pi over 4. So that's a positive value. Sine of pi over 4 is root 2 over 2. So I know that this is going to, I don't know what it is exactly, but I know it's greater than 0. Okay, so that is not, that cannot be our minimum value. So now we still have the option, would it be at time 0, time 2 pi, or potentially time 5 pi over 4? So let's work x of 5 pi over 4. So this was x of pi over 4. Let's work the algebra for x of 5 pi over 4. Well, that would be 1 over e to the 5 pi over 4, which is just positive some number approaching 0, times the sine of 5 pi over 4, which is negative. Ooh, okay, so I know then that x of 5 pi over 4 is less than 0. Okay, so this value, whatever it is less than 0. So is a number less than 0 less than the actual number 0? The answer to that is clear. It's yes. Therefore, this would be our absolute minimum output for x of t. Right? Our absolute minimum, which in this case is considered the time when the particle is farthest to the left. Farthest left at t equals 5 pi over 4. It doesn't require for us to find, again, the position, although we did. Right, this would be our position, or we could consider it, in this form. That's our position. But it's to the left of the vertical line x equals 0. Thus, we have justified, our justification actually comes in the whole process that we've executed here. So, all right, let's look at one more example. Okay, example number 4, AP problem, calculator allowed this time. Okay, so what I'm going to do is, first of all, I'm going to put f of x in for y1, and in for y2, I'm going to put the derivative with respect to x using math 8 of y1. So I would suggest that you do that, and then we'll come back and watch the rest of this. Okay, so first things first, anytime you see a function like f of x that we have here, and it looks like the derivative is going to get significantly messy, it's going to get pretty gross, what I would do is I would make sure you read the whole problem through, because likely it's calculator allowed. If it doesn't say calculator allowed, well, then you better get to it, but likely it will be. Okay, I've got my interval, so my candidates, I already know my ends. On my closed interval, that'll be x equals 0 and x equals 3. So right away, I could, if I wanted to, draw out my table. X f of x. This is not very clean. Probably should have made it better. I got a 0 and I got a 3. I don't know how many values I'll have in between, but I do know that. If I plug in a 0, I get ln of 1 minus sine of 0 squared. ln of 1 is 0, so that'll be 0. Okay, if I plug in a 3, I get ln of 4 minus sine squared of 3. Now, I don't know what that is, so this is where you would use your calculator and alpha trace y1 parenthesis 3. Let me get a value. Okay, when I plug 3 into y1, I get 1.366. Okay, 1.366. All right, now I got to do a little work to find those critical points. So in y2, clearly I plugged in the derivative of y1 with respect to x, and it should say here for x equals x, right? Now I want you to graph y2, and I want you to find the values for which that function equals 0. Those will be the values for which f prime, if you do that, that'll be where f prime of x equals 0. You also want to look at the graph and see if there's any values for which it doesn't exist. Okay, so it might be represented by a couple different visual things, like a vertical asymptote, or a hole, or a jump discontinuity, potentially. Okay, but I'm not anticipating that being a problem. Okay, so I'll sketch actually my graph of the derivative in just a moment. Okay, when I graph, I did a window, x min of 0, x max of, I went to 4. I went y min of -3 and a y max of +3. What that allows me to do is see this entire interval plus a little bit. And then it allows me to see where that function f prime would be crossing the x-axis. So here's what I got for a sketch. Let me draw y prime in a different color. Looks kind of like, oh, maybe I should put my labels on here. Here's 1, here's 2, here's 3, and it goes out to 4. I don't need to put 4 on there. So here's x equals 1, x equals 2, x equals 3. The sketch of f prime looks kind of like, oh boy, not to scale exactly, but it does something like this. Okay, so my critical points will be these two values. I'm going to call this x equals A. We'll call this x equals B. And I'm going to store them that way. Okay, I'm going to do a quick calculation and then we'll go and move forward. Okay, so I've found A. I stored A as, I believe, to 3 decimals. It was 0.398, and I went and just stored it as its entire number. If you got issues or questions on how to store, please see me or your instructor. I found B to equal 1.35, 1134, 838. Okay, so those are my critical values. So I'm going to then use those. And now there's a third value, right? There's a third point right here. We could call that x equals c. All right, however, it's not in this interval, so I don't need to use it. Okay, so now that I've stored, this is the power of storing these numbers. Now that I've stored it, I can find f of a. And I can find f of b, and then I don't have to re-input those into the actual function. So alpha trace y1 of alpha a, and that comes out to be, I can round this to 3 decimals, so it comes out to be 0.185, and alpha trace y1 of b comes out to be negative 0.098. It says find the absolute maximum and absolute minimum values of f. Okay, so I have my absolute max. I have an absolute maximum of 1.366. And I have an absolute minimum value of y of a. Now I can write it as y of a, y of b, because I've defined it as b here, which comes out to be negative 0.098. If you have not defined a and b explicitly as a number, then you cannot use that notation. Then you'd have to plug in that value, actual. Okay, but since I have defined them explicitly, and I should probably do this, I should probably call this, oh, that won't work, f of 3 and f of b. Okay, but those are my absolute maximum and absolute minimum values. All right, let's look at one more example at the bottom here. So back from 08, You see a number, a higher number on a multiple choice that's in the 70s or 80s or 90s. That means calculator allowed. That means calculator allowed. However, the calculator doesn't really help you here. It says the function f is continuous between -2 and 2. And f of -2 is equal to f of 2. Okay, so let's sketch. So the function is continuous. Okay, it doesn't say anything about being differentiable. But it does say that f of -2 is 0. And f of +2 is 0. Okay, it says the function, if there is no c value for which c is between -2 and 2, for which the derivative is 0. That means the slope never equals 0 anywhere, right? The slope of the curve never equals 0 anywhere. Which of the following must be true? Okay, so part A is saying that the derivative is greater than 0 for all k in between -2 and 2. Well, that couldn't be true, right? Because that would mean that like the derivative never, right? That would be a problem. Why would that be a problem? Because now the function is not continuous. Okay, part B, let's look at that one. Let's do that in a different color. It says then the derivative is always less than 0. Well, that's not true, because then again, function not continuous. Okay, it says for part C that the derivative always exists, right, between -2 and 2. It exists. Well, that's a problem, because we know that the derivative never equals 0. And since the outputs on both of the ends are equal to 0, that means that in order for me to do that, if the derivative always exists, whether it looks like that, the function looks like that, or like that, at some point, right, it looks like at this point here, or down here at this point here, that the derivative has to equal 0. So that can't be true. Okay, part D, let's look at that, analyze that for a moment. It says that f prime at k exists, but f prime is not continuous. It says for all values k between -2 and 2, the derivative exists, but the derivative is not continuous. That is a contradictory statement. In order for the derivative to exist for all values, then the derivative must be continuous. Okay, so that's out. That means that the last one has to be our answer. For some k, between there, f prime at k does not exist. Well, in order for me to get from -2, 0 to +2, 0 and keep the function continuous, I'll have to have like some increasing portion followed by some decreasing portion, or the other way around. But in order for that to happen and for the derivative to never equal 0, that means that at some value, right, at some k value, let's call this value here. Whoa, I don't want the highlighter, I want the pen. There it is. At some k value, f prime at k doesn't exist. Pretty abstract, conceptual in its nature, making you understand the idea of continuity, differentiability, and their connection, as well as, critical values and all that good stuff. So, all right, guys, that's it for, I think that's 4.1. Yeah, that's 4.1. Have a great day. See you in the next video.